Okay, so again, welcome back to Unit 3, WEP, Work Energy Power for AP Physics C. So we've been building all the way up. We talked about we talked about work, kinetic energy, potential energy. Now let's kind of bring it all together and talk about the law of conservation of energy. Okay, so one thing to remember is that energy is a conserved, not conserved, but a conserved quantity. This means that the total energy of the system does not change. So one thing to note, this is for an isolated system. Okay, which means mass and energy can't flow in or out. Okay, so when we talk about these systems, we have to identify everything in the system so we don't have to worry about is that energy there, is it not there? Okay, but what's going to happen, even though the total energy doesn't change, the individual energies will change though, okay, because you'll have a conversion. You'll have conversion from potential energy to kinetic energy. You'll have conversion from spring potential energy to kinetic energy and so forth. So work is done when energy is transformed from one type to another or transferred, right? So work, sometimes when we talk about it, work is the ability to transfer energy. Energy is the ability to do work. So they use each other in their definitions, right? And so the basic law, when we focus on conservative forces, right, we simply say delta U plus delta K equals 0, or we just say that the total energy before equals the total energy after, right? Where E at this point in time is just K plus UG plus US, okay? Now, we do have talking about these dissipated forces. So the general law, so the basic law has this delta K plus delta U equal to 0. But the general law will include these dissipative forces, and the big dissipative force that we're going to look at will be friction, okay? And what that'll do is it'll generate thermal energy, which we know as heat, right? And so now I can rewrite the law to say delta U plus delta K, so change in potential energies plus the change in kinetic energy plus the work done by non-conservative forces, i.e. friction, is going to equal 0. Okay, so last year in AP Physics 1, this is where you stopped, right? But now here in AP Physics C, I can't spell physics, okay? That's what we're going to end up with, okay? So let's look at an example, right? So here the example says we got a block of mass M sliding on a rough horizontal surface, which, and again, anytime you see the word rough, means there's going to be friction involved, okay? Traveling at a speed of v0 when it strikes a massless spring head-on and compresses the spring a maximum distance of k. If the spring has a spring constant of k, a maximum distance of x, sorry, not k. If the spring has a spring constant k, determine the coefficient of kinetic friction between the block and the surface. So this is going to be a derived question. So derive an expression for the coefficient of kinetic friction. Okay. So the way I like to look at this is we have a before side, we have the after side. I like to organize things. So before, right, on the before side, the only thing present is going to be the kinetic energy, right? So the only thing moving that you can see here is the block. The spring hasn't been compressed, okay? And then on the after side, we have the potential energy of the spring because it's been compressed at a distance of x plus the work done by friction, okay? So I can now just start substituting in equations. We know that this is going to be 1/2 mv0 squared. My spring is going to bring in my spring. Switched over to black. Is going to be 1/2 kx squared, capital X squared. Now the work done by friction is going to be the amount of friction times the distance that it displaces, which in this case, I can actually change this because it's just going to be x, right? Because it's going to move a distance of x, okay? And now I just start algebra, right? So I'm going to multiply everything by 2 to get rid of the fractions. I can't cancel the m's because my spring doesn't have an m, but here's what I'm solving for. So I am going to subtract kx squared over. All right, and so I'm going to have mv0 squared minus k times x squared equals mu mgx. Okay, and again, I'm going to solve for mu, so I'm going to divide by mgx. So I get mu equals to mv0 squared minus kx squared over mgx. Okay, now the good thing is you probably don't have to simplify from here, but if you want to, make sure you get it right. So I'm going to split this fraction. So it's going to be mu equals mv0 squared over mgx minus kx squared over mgx. And now I can just cancel things out. M's cancel. One of those x's cancels one on the bottom. So my final answer would be v0 squared over gx minus kx over mg. So that would be my coefficient of kinetic friction. Okay. So this involves a spring with friction, okay, but be aware that in this particular class, you could potentially see that work done by a non-conservative force, where most of the time the non-conservative force will be friction. Okay, so we have 2 more videos to get through. It's going to be power and potential energy diagrams.